Well, it's wonderful to be here in beautiful Santiago in beautiful Chile. And just as Paul has done astrobiology but talked about gravitational waves, I don't do astrobiology and I don't study stars and I don't study gravitational waves either, but I thought that it might be an interesting discussion for us to have to look at our place in the universe in terms of our place in both space and time. So that's what I hope to talk about today. And in particular, if the question is, are we children of the universe? I give an answer. And the answer is yes, we are stardust. And that's what I'd like to talk about today. From a personal perspective, I also have been familiar for many years with astrobiology through my late colleague Carl Sagan, whom I met when I was a student in Arecibo in 1973. As a matter of fact, I gave him a ride in a car and was so excited about that. It was just an unbelievable experience. And so Carl Sagan reminded us of this wonderful picture taken from the Voyager spacecraft at a distance of more than 4 billion miles from the Earth of the pale blue dot. And so one of the things I want to start out with is again reminding us that the pale blue dot that we know of the Earth is only a tiny microcosm of what we call the galaxy, which is again only a tiny, tiny, minute part of the universe. An important point to keep in mind is that the universe is much, much older than the sun is. And we think of the sun as very important, and we think in the terms of the time frame, maybe of our lives, maybe of historical time, maybe going back to the life of the million years that humans have been around, and going back, following geology through the history of the Earth and the sun. But the Big Bang occurred far before that, 13.8 billion years ago. And let me also remind those of you who don't understand when we say what a billion is, it's 1,000 million. The sun, again, is much younger than that. So we have to keep that in mind. During the period after the Big Bang, the universe was expanding. It was also cooling down. And a great thing about astronomy is that we are able to explore not only the expansion of the universe in terms of space, but also time, because we measure light photons which travel to us at a finite speed. So the further out we look, the longer the light we see has taken to reach us. So not only are we looking out in space, we are also able to look back in time. So what we want to do is try and understand what has happened since 13.8 billion years ago to the time when the sun was formed, the sun in the solar system, about 4.5 billion years ago. One of the events that was very important in the context of my talk is that within about the first 3 minutes after the Big Bang, so 13.8 billion years minus 3 minutes ago, protons and electrons fused to form nuclei, and some of those nuclei, which were the hydrogen nuclei, got together and formed helium. But as I said, the universe was expanding and cooling, and after about 3 minutes, the universe got too cool and further fusion could not take place. So a very particular constraint that we can place on how the Big Bang happened and what happened after that is that of all the atoms and nuclei that we have in the universe today, helium makes up about 25% of the mass, and hydrogen makes up about 74% of the mass. It was about 75% at the end of the 3 minutes. It wasn't more than that, it wasn't less than that, it was exactly that division between hydrogen and helium. And furthermore, there was no carbon, there was no iron, there was no oxygen, there was no nitrogen. And so we're going to use that information to learn more about what has happened since the end of that first 3 minutes. So the question that I want to pose tonight is, where do I come from? I'm made of carbon. The air that I'm breathing is mostly made of nitrogen and oxygen. So where did they come from? They weren't made in the Big Bang. And what can that tell us about our place in time today? So remember that we are a carbon-based life form, but that carbon wasn't made in the first 3 minutes. Again, we want to focus on the time frame between 13.8 billion years ago and 4.5 billion years ago when the sun formed. That's a lot of time in between those two. A lot can happen. A lot went on. And so keep that in mind as I continue to talk. But let's step outside for a minute and look up at the sky. So this is a picture taken above the ALMA array, looking up at what you actually see in the sky. This band across the sky is called the Milky Way galaxy, and what we see is a band. That is the disk of the Milky Way galaxy, and it appears as a band because we are inside it. Let's see if you can understand why that is. So first, let me explain what a galaxy is. This is a picture of a galaxy which is called Messier 81. So it's number 81 in the catalog of Charles Messier. Astronomers often aren't very clever in how they name galaxies. What do you see in this picture? First of all, there are some objects that show spiky things outside. Those are stars in our galaxy. And we are inside a galaxy, so to see other galaxies outside it, we see things in our own galaxy. The trees in our own forest are in the way, if you want. Some people like studying those stars. I hate them. I like galaxies. But this is a galaxy that we think, this is what the Milky Way would look like if we could step outside and look back at our home. And you can see a couple of interesting things. In the center, you see something that almost looks solid. It's not a solid object. It's just in the center of the Milky Way, there are so many stars packed so close together that it appears as a solid because you can't see individual ones. As you go further out, you see more structure where the density is lower. So now, the next question is, where would the solar system be in this galaxy if this were the Milky Way and I was looking from the outside? And so here it is. In fact, we in our Milky Way live kind of in the suburbs, kind of towards the outside. And that actually might be an important part of why there's life on our planet. Now think again, imagine that you are in that location in the galaxy, and you're looking up at the sky. When you look along the thin disk of the galaxy, you see a lot of stars. When you look up or down, you see many fewer. And that's what you see when you look at the night sky. The reason it appears as a band is because we're in the middle of it. It wasn't until 100 years ago that people realized, astronomers realized, that we were inside this structure called the Milky Way. So I've already said that lots of stars, the Milky Way contains billions and billions of stars. In fact, a lot of those stars are older than the sun. The Big Bang took place 13.8 billion years ago. The Milky Way was formed something like 13 billion years ago, and the sun was only formed 4.5 billion years ago. So during that intervening 9 billion years, lots of other stars formed, and therefore they are older than the sun. Another point about the sun is it's very special to us, especially those of us who live in the northern hemisphere, where the other day it was minus 12 centigrade. It's a little warmer here, thankfully. That's why I came. The sun is an average star. Other stars are bigger than the sun, or smaller than the sun, or more massive than the sun, or less massive than the sun. The sun is kind of a typical average star. Now, just to put ourselves in perspective again and give ourselves a sense of scale, because the universe is a very big place, let's take a look at a little region of the Milky Way. Let's zoom in on it. This is a region where stars are being formed today. So not only are there stars older than the sun, there are stars much younger than the sun that are just forming today. Also note that we see dark regions and bright regions. This is a photograph taken with an optical telescope. The bright regions are is from starlight. Stars shine. But you also see dark regions. And you see them as dark because they consist of cold molecular gas and dust, which does not shine. Rather, it blocks from any stars that might be behind it. So we have to, when we interpret a picture like this, understand that the bright areas are stars and the dark areas are just as important in our story of how stars form. It's the cold gas and dust out of which stars and planets and life will form in the future. So let's zoom in a little more on our picture. This is the famous Eagle Nebula picture taken with the Hubble Space Telescope. Again, to point out what you're seeing is the bright regions are newly formed stars. Those stars may only be a few million years old. And the dark regions are cold dust clouds or dark clouds out of which stars will form in the future. Let's zoom in even further. So we zoom in again and on the edge of one of the pillars, and you can see regions where starlight is getting out and regions where the stars haven't formed, or at least the starlight can't get out. Let's zoom in even more on this little tiny piece, and that just shows you the size of the solar system. We're not very big. The universe is a really big place. So back to our picture of the night sky. The disk of the Milky Way, our galaxy, appears as a band because we're inside it. Starlight shines. Dust is also very important, but it doesn't shine. Rather, it blocks out the light. So here's a zoom in on a place which we think will be the birthplace of stars in the future. The dark stuff, again, is the cold gas and dust, which is the stuff out of which stars are made. And the important thing is that the dust itself, while it blocks and obscures the light seen at optical wavelengths, actually gives off radiation that radio telescopes, specifically ALMA, can detect. So optical telescopes like Hubble, the VLT, Gemini, Magellan, the LSST, and the EELT, astronomers are very good at obscure acronyms. They see the starlight. ALMA offers a different view of those star-forming regions by detecting the cold gas and dust, and therefore telling us about the stuff out of which stars and planets might form. Now we have to go back and think about the ecosystem that we have in the Milky Way galaxy, that stars are born, and they live, and they die. Stars are born when those cold molecular and dust clouds collapse because they have mass and they're drawn together by gravity. And when a gas collapses, it heats up, and it will reach the point where the fusion of hydrogen into helium can take place again, and then the star is formed, and the star shines. As stars live and later on die, they get hotter in their centers, and they're able to fuse other elements. In that sense, the sun actually isn't very interesting to us, but more massive stars are actually able to form not only helium, but also carbon, oxygen, nitrogen, iron, magnesium, all of the things and all the rocks that we have here on the Earth. And again, a point is the sun, not only is it average, it's also middle-aged. It was formed about 4.5 billion years ago, and it will probably live stably, generating its nuclear fuel and causing it to shine as we see it in the sky today for something like about another 5 billion years. And after 5 billion years, the sun will run out of hydrogen, it will have converted into helium, it will have also taken some of that helium and formed it into carbon, but then the game is over, and the sun will die, and its outer layers will explode, and we'll get something like the picture of the planetary nebula, as we call it, that you see. More massive stars are interesting. This was referred to by Paul. More massive stars explode catastrophically in what we call supernovae. They also have been able to convert more of their light elements, hydrogen and helium, into the things like iron, carbon, magnesium, and oxygen. And so when they explode, they take all of those elements and they throw them out to large distances, polluting the clouds that will form the next generation of stars. So over the 9 billion years between the generation of the first stars to the time the sun formed, previous massive stars lived and died, and they polluted the dark dust cloud out of which the sun formed. So today, in fact, we are literally stardust. We are the end product. The carbon in our bodies, the oxygen and nitrogen in our bodies were made in an earlier epoch in the history of the Milky Way galaxy and the history of the universe. This diagram is just meant, from a technical point of view, to show us that all of the elements which are blocked out in blue there were manufactured in supernovae. The yellow ones were manufactured in massive stars, and it's only the very light ones that are made in stars like the sun or in the Big Bang. So very literally, we are stardust. The carbon in our bodies was manufactured in previous generations of massive stars which lived and died before the sun was formed. So that's my first message, but now let's think about that just for a minute. In massive stars, the ones that are important to forming supernovae, today, those stars already have some carbon, nitrogen, and oxygen, and in fact, they use that in order to control their thermonuclear fusion of hydrogen into helium. So one of the things that we do not understand is how the first stars formed and underwent their thermonuclear process. So I've told you a story about star lives, and we think we understand them for later generations of stars. In fact, we don't understand when the first stars formed, why they formed, and how they formed. It's also true that we've talked about the fact that we're a carbon-based life form. We don't know whether that's the only life form that you could have. Maybe there could be a life form that was based on something else, like silicon, for example. And a third point is, if we are a carbon-based life form, then in order for us to form, that carbon had to be there, which means there had to have been the successive number of generations living and dying to make the carbon that ended up in our bodies. And so we can also ask a sort of uncomfortable question about, is the reason that we are here on Earth today because the universe had evolved for 9 billion years before the solar system was formed? I'm not going to answer those questions. Instead, I'm going to point out, especially for younger people in the audience, that astronomy is full of questions which we can't answer today. I think that's good. That's what excited me when I first started to do astronomy and heard Carl Sagan give a lecture about the pale blue dot. I I didn't end up being that interested in planets or astrobiology, so I went in a different direction. But certainly, having the idea that we don't understand fundamental things, but that we have many of the tools that will allow us to get answers to those questions, is what led me to study physics in college and university and to become an astronomer. And I just also want to point out that Chile is blessed with some of the best viewing on the planet. And so many of the most sophisticated tools, like ALMA and the other observatories, are right here locally. And the rest of the astronomers in the universe, thank you for that. Thank you very much.